You may have been wondering how it is that packets find their way across the network from your computer to their eventual destination. And so in this unit, we're going to learn how it is that routers know where to send the packets next. In this first video, you're going to learn about some general techniques and approaches. And then in later videos, we're going to dig into some of those techniques in a lot more detail. The basic problem that we're trying to solve is, what path should packets take from A to B? Should the path be picked by the end host A, or by the routers, or by some central external controller? Which path should we pick, and on what basis should we pick it? For example, should we pick the shortest path, the least congested path, a randomly picked path, the safest path? There are many choices that we have. You might want to pause for a moment and think about the techniques that you might use to decide which path a packet should take. You might want to pause the video and think about it for a few minutes. So there are very many techniques that we could choose, but there are a few common approaches that are used very widely in networking and in the internet in particular. And these are used to route packets to their destinations. We're going to take a look at each of these in turn. The first is called flooding. Flooding is a simple way to make sure that at least one copy of a packet is delivered to every destination. Routers forward an arriving packet to every interface except the one through which it arrived. Let's take a look at an example. Packet from A is sent by the first router to all of its output links and so on through the network. It does this except for the one that would send it back to A again. You can see that the packet is eventually going to get delivered to every link in the network, including every link, and therefore to every destination, including B, the one that we want to send the packet to. If the packet contains B's address, then B can simply filter on packets matching its address. But we can also see if there are loops in the network, then the packet's going to be delivered multiple times. Once over every link, and then again and then again, and the packets can potentially loop forever. So the pros and cons of this approach are that the packet reaches the destination along the shortest path, and flooding will work when we don't even know the topology. We didn't need to know the topology, and we didn't need to put entries into the router's forwarding tables for our examples. It's nice and simple. Flooding is often used when we don't know the topology, for example, when the topology has changed. There are some obvious shortcomings to flooding. Flooding is nice and simple, requiring no state and no tables in the router, but because it's so inefficient, it is really only used when we know nothing about the topology at all, if we can't trust our knowledge of it, and we're trying to reach every node. So packets can loop forever, as we saw in the example. This is why we have the TTL field in IP datagrams, so that if a packet accidentally gets stuck in a loop, it'll eventually be deleted. Flooding is clearly very inefficient. Even though we wanted to send the packet only to B, it was sent over every link to every end host, many times. And because packets are delivered to everyone, there are some clear security implications. Everyone can see all the packets. If the packet isn't encrypted, this is clearly not very secure. Source routing is when the source includes a list of the routers that the packet should visit along the path. Let's take a look at an example. When the source has put a list of routers, R1, R2, and R3, into the packet header. When the packet reaches R1, what it's going to do is to pop off the first entry and send the packet on to R2, and so on. The benefits of source routing are that the source gets to pick the path. It's free to pick any path it would like, avoiding congestion or parts of the network that it doesn't trust or doesn't like for some reason. It's easy to avoid loops if the source knows the topology. It simply makes sure that every router appears only once on its list. And there's no need for tables in the routers. There's no state to build and no state to maintain at the routers. They're kept nice and simple. So the source needs to know the topology, which means that there's a lot of information that needs to be sent to every end host, particularly when the topology changes. And if the network has a large diameter, the list of routers can get quite long, potentially creating large inefficient headers in all of the packets. For these reasons, and as end hosts get more powerful in the future, some people believe that source routing will become much more popular. There's some evidence that big cloud providers are starting to use source routing ideas in their own data center networks. You can even make an argument that it's a good example of the end-to-end principle. If you can place the function at the end of a network rather than in the middle, then you should, unless there's a good optimization reason to put it in the middle. In practice, as you probably know, routers do use forwarding tables. We can think of these as merely an optimization so that the end hosts don't need to worry about the topology. But it is interesting to note that, strictly speaking, routers don't need to know the route that a packet takes. The downsides of source routing are pretty clear, so you won't be surprised to hear that packets are not usually source routed over the internet, but the IP protocol actually has an option that allows the end host to specify the route of a packet by giving it a list of routers to pass through. Unfortunately, most part of the internet don't support this option because of the security implications. The owners of different parts of the internet would rather decide the path of our packets, the path that our packets take for us, and not expose the internal topology of the network. The most common way packets are forwarded by routers is using a local forwarding table. When we send a packet, it's routed hop by hop to its destination. Each router looks up the destination address in the packet header in its forwarding table. So for example, this packet here is addressed to B. When we transmit it, the first router will look up the address in its local table, and it sees that router R2 is the next hop for packets with address B. R2 and R4 are going to do the same thing, and the packet is eventually going to be delivered to B. We can think of forwarding tables as an optimization. The network handles hop-by-hop routing on our behalf and therefore saves the end host from having to figure out the path of its packets or to know the topology. But it does come at quite a cost for the routers. It requires us to populate the forwarding tables. Most of the remaining videos, in fact, in this unit are all about how to populate those forwarding tables. Purists like to point out that it requires the network to keep per destination state. In other words, we need to populate the tables with enough information to reach every destination in the network. At least it's not per flow information, but still, it takes quite a lot of work and it's error-prone to populate these tables. In fact, armies of engineers keep the internet going by keeping a close eye on how the routing tables are populated. So, routing means picking the path that a packet takes across the network. In general, there are many paths between any pair of end hosts. For example, just between source A and destination X, there are many different paths we could choose. I've shown only some of them. You can find more. So, which path should we pick? There are two basic properties that we need. First, we need to find paths such that every host can reach destination X. And second, we need the paths to be loop-free, else our packets will get stuck in the network. And therefore, it's helpful to think in terms of spanning trees. Spanning because it reaches or leaves, and a tree because it's loop-free. So for example, the green tree that I'm showing here is a spanning tree rooted at X. If we want to deliver packets to X, we simply need to make sure that the packets jump onto and follow the spanning tree. And as we'll see later, there are many ways to build spanning trees using a central or a distributed algorithm. So note that there's a separate spanning tree for every destination. In my figures, I'm only going to show the spanning trees for one destination at a time, in this case X, just to keep the figures a little bit more understandable. But remember, there are also spanning trees to reach every destination in the network. So one question we must consider is which spanning tree to pick. There are usually many spanning trees. For example, the orange and the green trees are both spanning trees rooted at X. Which one should we pick? Which is the best for what we're trying to accomplish? One natural and common choice is to pick the spanning tree such that each source reaches X over the shortest path, which means that the path with the fewest hops. We call this the shortest path spanning tree. Of the two spanning trees in our example, the green tree is the shortest spanning tree. Note that it's only the shortest path spanning tree. It's only one of the shortest path spanning trees. There are actually several of them. We still have to choose from amongst several. Another common approach is to assign each link with a weight or a cost to use that link. For example, the cost might equal the length of the link or the inverse of its data rate. We'll see some more examples shortly. But if we assign costs, we can pick the spanning tree such that each source reaches X by following the lowest cost path. This is called the lowest cost spanning tree. It's also called the minimum cost spanning tree. So in this example, I've assigned a cost of 1 to some of the links and a cost of 100 to others. So in this case, the orange tree is the lowest cost spanning tree because it uses only links of cost 1, whereas the green tree uses links of cost 100. You may be wondering what are good cost metrics for the links. In general, we have many choices. We could pick, for example, the cost that we are charged for using the link. For example, network operators charge customers to use their network and could potentially charge more for using certain links, such as those going underneath an ocean or over a satellite link. The cost could be based on the length of the link. We might do this to encourage use of the shorter paths. Or the cost could be based on the data rate to encourage us to use the faster links. Or it could be based on how congested a link is right now, or how congested it tends to be at this time of day. It could also be based on the reliability of the link. If we know, we might prefer to use more reliable links whenever possible. In fact, it can be based on any value we pick that's picked by the owner and operator of a network. But note that if we assign the same cost to every link, then the shortest path spanning tree is the same as the lowest cost spanning tree. Here's another example of a lowest cost spanning tree. I assigned different costs for the links this time. So I just want to show you this as an example. This time the solution is slightly less obvious, but you can still see easily, and you can still solve it easily by inspection in just a few seconds. The purple spanning tree is the lowest cost spanning tree, and so packets from A, B, C, and D should follow the purple tree in order to reach X over the lowest cost path. But finding the lowest cost path is not always so easy. Imagine in this network here. Clearly, this is way beyond something a human could do in their head. Well, me at least. Maybe you can. So we need automated algorithms to calculate the path and to put the necessary forwarding entries into the tables in the routers. To calculate the paths, the routers will exchange information with each other about the current technology. We run a routing algorithm, sometimes called a routing protocol, to decide what entries to put in each of the router's tables. We're going to be studying different routing algorithms in the next few videos. So far, in all 4 approaches, we've assumed that packets always follow the same path from a source to a destination. It means some links will tend to get congested while others are not. For example, if we build a spanning tree, then packets will follow the tree. Links that are not on the spanning tree might not get used at all. So one thought is to spread or load balance packets over all of the links, reducing the congestion on the network. So this is called multipath routing. So far, we've assumed that all packets to a destination do follow the same path, and in particular, the shortest path or the lowest cost spanning tree. The downside of the shortest path spanning tree, as I said, is that some links become very popular and can themselves become congested, which means we might need to keep adapting the algorithm. So this alternative approach is to spread traffic to a destination over several routes or paths. Essentially, it's load balancing traffic over some or possibly all of the paths. In my example, there are 2 spanning trees routed at X, the green one and the orange one again. The idea is to use both spanning trees, and possibly more spanning trees if we would like and if they're available. The routers would contain 2 or more forwarding entries for each destination, and then randomly pick between the entries when deciding where to send a packet next. In my simple example, traffic sent to X is now spread over 11 links instead of only 6 links if they always followed the green tree. If we're sending the same amount of traffic as before, it means each link will be less congested with traffic going to X. Multipath routing is actually very commonly used by internet service providers to load balance the traffic across their networks to reduce congestion. When you've played around with traceroute, you've probably seen examples of probes that came back from different routers representing different paths. Multipath routing is also commonly used in data centers to spread traffic over different paths to reduce congestion and hence minimize delay that might otherwise slow down a big distributed application. Another assumption that we've made so far is that we only want to deliver packets to one destination. We call this unicast routing. There are cases when we want to send a packet to multiple destinations. One packet is sent to multiple destinations in one go. For example, imagine we're distributing live TV of a sporting event over the internet to lots of current viewers. It would be very wasteful to send the same packets multiple times from the source, particularly if there are millions of people watching the same event. So it's worth asking if we can use a spanning tree to ask the network to replicate the packets on our behalf. And we call this multicast routing. The packet is routed to multiple destinations in multicast routing, and the network replicates the packets for us. In this example, the packets are sent by source X. X sends only one packet, and it's replicated through the network according to the spanning tree, along that spanning tree, so that every copy travels over the spanning tree to all four of the destinations. Because the packet follows the spanning tree, there's guaranteed to be no loops, and only one copy of the packet is sent to each destination. So it's a nice use of the spanning tree again. Multicast routing means the routers have to do more work for sure, and they're essentially saving work for the source by replicating packets in the network on its behalf. Multicast routing is therefore an optimization. It's not strictly necessary, but it reduces the number of copies in the network, and so if there's lots of multicast traffic, it can be worth doing. But we'll see later, it's pretty complicated, and some people think the effort is just not worth it. So in the previous example, the packet was delivered to every destination. That was really an example of broadcast, not really multicast. The packet was delivered to everybody. In practice, we're more likely to want to send a packet to a subset of the destinations, those currently subscribed to the group, something we call a multicast group. So for example, if I prune the tree to remove one link, source X is going to deliver a packet to only A, B, and D, but not C. I've shown the green spanning tree for this set of destinations, and you can see how the packet is replicated so that it only reaches destinations A, B, and D this time. In general, multicast routing is a lot more complicated than unicast routing. You'll learn more about multicast routing in a special later video. And so in summary, there are several ways to route packets across a network, starting with the simplest method, flooding. In practice, we use routing algorithms, or also known as routing protocols, to calculate routes. It's common to find the shortest path or the lowest cost spanning tree. Once we pick a tree, we populate the forwarding tables in the routers so that the packets will follow that spanning tree. Other types of routing include multipath to spread traffic over many links, and multicast to deliver packets to multiple end hosts in one go.